First lecture this morning is Hitoshi Murakami from Introduction to the Volume.
Thank you for inviting me to this wonderful workshop.
And
Please, first of all, I'd like to tell you that you don't need to copy the slide. I will give you the PDF file if you want later. And good news for us all, it is that an officer at the passport control of the Kennedy Airport is a great fan of mathematics. In fact, he knows free manifold, quantum invariant, the Jones polynomial, Alexander polynomial, the chord diagram, and my name. He knew my name. So it's great news, at least for me and for you. So let's start. I'll give you introduction to the volume projection. And this is the plan of my talk. And I start with the definition of very representation of a link. As you may know, that every link can be expressed as the closure of a braid. This is a braid. So here we have three strands from top to the bottom. And if we take closure, it means that we close all the strings and make knot or link. And this is the closure. And Alexander's theorem states that every link can be presented in this way. And more precisely, an M braid is a group by putting up and down the two. It is a product. And it has generators, N-1 generators. M braid has N- generators. And the relations are, the important one is this. It is called the braid relation. You can easily see that these two present the same link if you close it. And so in this way, one can make a link from braid, but it may happen that two different braids make the same link. So when does it happen? It is a theorem by Markov. So this theorem says that two braids give the same link if and only if they are related by a sequence of the following moves. One is the conjugation as a group. So we exchange two paths, alpha and beta. And second, this is not so the first group is a group theoretic, conjugation is a group theoretic conjugation, but stabilization is not a group operation because the number of strings are different. In this picture, this is the 3 braid, and this is the 4 braid. What I did is just add an extra generator, sigma 3 in this case. In general, if beta is an n braid, we put n generator to the bottom. So this, the right-hand side is n plus 1 braid. And it's easy to see that if we close the last string, then we can twist it and shrink it to a trivial strand like that. So these two, it is easy to see that these two give the same link. And the point of Markov theorem is that for any two braids that give the same link can be related by a sequence of these two moves, conjugation and stabilization. Okay. And next, I will tell you how to make a link invariant from braids. It is called Yang-Bax operator. So let us prepare an n-dimensional vector space over C. And so R, which is called R matrix, it is endomorphism of V tensor V. And U is again an endomorphism. In fact, it is an isomorphism of V and A, B non-zero complex numbers. Then the quadruple R, mu, A, and B is called an enhanced Yang-Bax operator if it satisfies the first. This is called the Yang-Bax equation. I will tell you later geometric interpretation of this equation. And second, mu. So mu is a endomorphism on V. So mu tensor V, mu tensor mu is an endomorphism on V tensor V. So R and mu tensor mu communes. And third, if you take the trace of R times identity tensor mu, then it is a scalar multiple of the identity, where trace 2, tier 2, is it is a generalization of the usual trace of a matrix. It so M is an endomorphism of V tensor V. So if we fix basis, then it can be given as a matrix like this. So here, yes. So this is the matrix. Yes, and the trace 2 is just a reduction. Second. Yes. Trace 2? Yes. Sorry, thank you. Endomorphism of V tensor V2, endomorphism of V. Thank you. So, yes, so M is an endomorphism of V, then trace 2 is an endomorphism of V itself. And it is given by this matrix. So this is this presents a endomorphism of V. So our usual traces can be said as trace 1, and it is given by, so if endomorphism on V is given by N sigma I and sub J, then the trace is given by the sum of N I. So, and if we are given a enhanced factor, and then given a break, we replace each generator with R or R inverse. So if you have a generator here, a positive crossing like this, then we replace with the R matrix. So this shows that R is a homomorphism from V tensor V to V tensor V. And the same is for negative crossing. And by replacing at each crossing, we have given an n break, we have a homomorphism from V tensor n4 tensor V to itself, like this. So here we have a free break, and we have 4 crossings: positive, negative, positive, and negative. So we replace positive crossings with R matrix and negative crossing with R inverse matrix. So this is a 3-fold tensor endomorphism of 3-fold tensor of V. Okay. Now we can define value. So suppose that we are given a link link L, and which is given by an n break theta. Then the T invariant here is by definition like this. So phi of beta is an endomorphism of, in this case, n4 tensor of V, and we multiply by n4 tensor of mu. And then this is an n-morphism of n-fold tensor of V. And we can take trace n. We can reduce the final index, a pair of final index. And then take trace n minus 1, taking trace n gives you n minus 1-fold tensor of V, n morphism of n minus 1-fold tensor of V. And then take trace n minus 1, which gives an morphism of n minus 2-fold tensor of V, and so on. Then finally we take trace 1. This is the initial trace, so we get a scalar here. And then we multiply scalars. Then this gives a scalar. And in fact, this is an invariant of a ring. So this is how we construct the invariant. So by closing, so in the braid, we take closure by closing the, sorry.
So instead of taking all these partial traces successively, we will just take the ordinary trace of this endomorphism regarded as an endomorphism from V tensor n to V tensor n. I mean, since phi beta mu tensor n is an endomorphism of V tensor n, if you just take the trace of that, you should have the same effect.
We have to be careful which. So we may regard this as a huge matrix.
Yes, sure.
But it's so it is a kind of diagonal. Yes, you're right. But yes, you may say so. Yes, yes.
What is the role of mu?
I'll tell you later. I'll tell you later. Oh, yes, I'll tell you later. So given a braid, so we close the braid. Instead, here we take trace. So the closure here indicates taking a trace. And so we replace all the crossing with R first, and we put mu at the bottom, and then take traces. Okay. This is how to make the link invariant from enhanced Yang-Bax operator. And this is indeed an invariant. So I'll show you very roughly the idea of the proof. So what we have to prove is that, of course, T is invariant under first the braid relation and the conjugation and stabilization. So we first prove that it is under braid relation. So this is the essential relation of the braid. So we have to drop this. And this is the picture of the system. So sigma I plus 1, sigma I is equal to sigma I plus 1, sigma I times sigma I plus 1. And in the operator, this is given like this. And this is exactly the Yang-Bax operator. Because you see, at the level here, we have R tensor identity. The straight line indicates the identity. So R tensor identity times identity tensor R times R tensor identity is equal to identity tensor R, and so on. So this is exactly the yes, Yang-Bax equation here. And this corresponds to the braid relation. So we have done invariance under braid relation. Next we show invariance under conjugation. So conjugation is just exchanging alpha and beta. And in the invariant we have, so we first replace alpha with phi of alpha by replacing each crossing with R and the phi of beta, and we should put mu here. And because trace is invariant under conjugation, which can be easily proved as a usual trace, so we can take phi of alpha here, because we can exchange this part and this. So we have this. And next we apply the second requirement of the enhanced Yang-Bax equation. It is commutativity of mu tensor mu and R. So we can make mu. So mu tensor mu go through all the way through E of alpha, because we have many R or R inverse here, but we can at each crossing we can pass mu tensor mu through R. So these mu's can be in the photon field.
Altogether? They have to all go together?
No, one by one. And so this is just a conjugation of with the and we have to do and finally prove the invariance under stabilization. So stabilization is just add an extra generator at the very bottom here, and we put mu's here. And so this is the form of the operator, and we look at the, because red, it's brown, anyway, this brown part. And so this is just the requirement of the third requirement of the enhanced Yang-Bax equation. So we can remove it. So the third requirement of the enhanced Yang-Bax equation is removal of this part. So we remove so here we have 4 grades, but we have 3 grades. And we have AB here. So we need mu here to make it invariant under stabilization, not only R matrix. So by adjusting A and B, so we add, in the definition of T, we add B to the N. N is the number of grade, and we multiply by A to the minus W. W is the algebraic sum of the exponents. So if we remove R matrix, then we have to multiply by A, and if we remove R inverse, we have to remove. We have to multiply by A inverse. So I need algebraic sum of the exponents here, and the number of strands here. So this proves that T is a linking factor. Yes.
Do you have in this picture a linear isomorphism between B and B star?
Sorry, say again. Sorry.
Do you have an isomorphism between B and the dual? No. But for calculation, we need a fixed basis. So by using that basis, of course, we can make an isomorphism. But theoretically, we don't need any basis. Does this answer your question? I was wondering if there was a natural isomorphism which you can construct using the mu and the
In general, not because representations are knocked out.
Yes. So, okay, I'll tell you later soon how we can make a matrix from the algebra and its representation. Yes. So,
Hitoshi?
yes.
So these are invariant oriented units.
Yes.
So you don't need isomorphism with B and B star. You don't care how they behave if you change the orientation. They can behave.
But maybe his question is different. Anyway, let me go forward. So, what did we say by quantum G invariant? So here is the D algebra, and V is one of its representation, irreducible representation. Then there's a theory that constructs an enhanced Yang-Bax operator by using these data. And that is called the quantum GV.
inference. So of course we can use dual representation and so on. So make many inference from various algebras. And in this talk, I will use quantum essay to see Vn infinite, which is called the n-dimensional Carter-Jones polynomial, and I denote it by J n of Q. And Q is a complex parameter, which, so you may regard it as just a complex number, or the complex parameter. And note that the Vn here is the n-dimensional irreducible representation of SL to C. And if n capital N is 2, it is the ordinary Jones polynomial. And we normalize our invariant so that for the unknown, the invariant is 1. To be more precise, V is, yes, n-dimensional vector space. And R matrix, so if you fix basis, R matrix can be written in this maybe too complicated formula. And here, a curly bracket of n is q to the m half minus q to the minus n half. And factorial of that curly n is something like the usual factorial. Yes.
So even though this is a sum,
yes,
it looks like a sum, it is not a sum.
No. So
There's only one
this
zero.
is the Kroneker's delta. So most of them are 0. So you don't need to worry so much. but if you want to write this in a matrix form, you need a sheet for two-dimensional representation. Anyway, if n is 3, it is big enough for calculation. But yes, and mu is given like this. Again, this is the Kroneker delta.
Excuse me.
Yes.
Can you go back to the previous slide just a second?
This one?
Oh.
Oh. Okay. You want to copy this? So I can give you the PDF file later. So our notation is like this. So if we give E, if EI is a given basis, then the R matrix is of this form, and RIJKM is and A is q to the x squared minus 1 over 4, and B is 1. And these data given enhanced Yang-Bax operator and give you the Carter-Jones polynomial. And in a general definition of T invariant, I dropped this one, but I did this to normalize it because without this term, suppose that here is F and this should be F. If we have a single strand, it is one braid, then it gives the unknown. But if we take the trace of the unknown, it is the sum of each entries of mu. So this gives you capital M, a curly bracket of capital M. So over maybe bracket, curly bracket of 1. So we need to normalize it so that for the unknown, it is 1. This is just a normalization.
Hitoshi,
Yes.
for which n is this practical to compute for, say, a 5-crossing number?
This has been implemented.
So for example, if you want to prove that this is indeed an enhanced Yang-Bax operator, we can work it for any n, for general n. But if you really
need to yes.
It's not Atlas has a program written by Torre.
Oh, yes.
And also another program.
But by hand
Computes.
computing, you mean?
Yeah, okay, but what's the practical for
How many crosses?
5 crust?
About 10. N equal 10.
So anyway, it is a good program to, good exercise to prove that it is indeed enhanced Young-Mass operator. Yes.
Is this the most practical way to compute it?
Of course, it depends. But for the proof, no.
Individual example.
For an individual map, for a given diagram.
That is not here.
Gregor is sleeping.
He is probably on the plane.
No, he's right there.
Oh, he
So I.
jet lag.
Gregor must do you like this formula to compute for a given individual node, or do you prefer Habermas method?
No. Habermas method does not work for all nodes. But there is a second program in the node atlas which uses a planar projection of the node, not a braid presentation, which uses less crossings in general. It's a little faster.
But you can prepare a formula for twisted crossing. So I assume that at each crossing, two strands goes down. But if it goes to the right, then we need another formula. So we need to prepare many formula and calculate. So it's complicated. So you will make mistake.
No, it has been implemented on a node atlas and checked against the two formulas
Yes, you're right.
for 10 crossings and color 5. So.
But anyway, I recommend you to start with this formula. So make a braid and then calculate. So to start with, we can calculate the formula for the figure 8. Yes, this is the figure 8. And this is not so hard to calculate the color zones. Any questions? Can you calculate the color zones for at least the figure note? Any questions? Yes.
I'm sorry, where does the information of the representation come in this formula? I don't see.
So we can use so-called quantum group theory to make an R matrix. So it is known how to make a solution to Yang-Baxter equation by using these classical data.
Okay, but the one used on the next slide is that's for this yes, for specific test.
Yes. Well, of course, there's a long history, but I can't tell you.
Okay.
Any more questions? Yes.
So for the ones that you get from the quantum groups,
yes.
do you always have B equals 1 or?
N equals?
B equals 1. Can you always assume B equals 1?
No. So this is. Sorry, I forgot where it comes from. But in general,
I think one can sort of normalize this using our matrix is actually that I don't know if the form of the there's a two-line paper.
Yes. So you can calculate if you want. So R is essential, and mu is next essential. And you can calculate A and B from the 3 requirements, maybe the 3rd requirement. Any other questions? So we can now know how the color-Jones polynomial is defined. So we go to the Abhijit conjecture. So the volume conjecture first proposed by Kashev in terms of his own invariant. But it turns out that his invariant is this specialization. The Jones polynomial evaluated at n root of unity. And so his formula, his conjecture can be expressed in this way: 2 pi times the limit of log of the Jones evaluated at root of unity over n. The limit of this is equal to the volume of the knot complement. And Stoltzfus assumes that n is odd. Anyway, okay, so we know the reference side, even though we don't know whether the limit exists or not. But we know the definition of the reference side. So what is the right-hand side? If the knot K is hyperbolic, we can define its volume. But how we can define the volume if the knot is not hyperbolic? So the definition of the volume of the knot complement is given by so-called simplicity volume or Gromov law. It is by definition the sum of hyperbolic volume of the hyperbolic pieces of the knot complement. Then what is the hyperbolic pieces? It is given by this decomposition known as Johansen decomposition. So it tells that any knot complement can be uniquely decomposed into sum of hyperbolic pieces and cipher fiber pieces. And the unit is given by pasting along tow line. So I give you an example. So this is, can you see, it is too small. So it is, you can see the figure knot, but we make a so-called 2-1 cable along the figure knot. So we go twice along the figure knot and make a half twist. And this is a knot, and this is not a hyperbolic knot. But we can decompose the knot complement into 2 pieces. One is hyperbolic and the other is not. So we can see the torus given by the figure knot. And so we first make a thick torus, like bagel. Yes, bagel. So I didn't know what is bagel. Now I guess it's like a bagel. And in the bagel we have so we have a circle running twice along the bagel. So we make it immerse a circle in the bagel, which gives a 2-1 cable of the figure. And we go backward, then we decompose the knot complement of this into 2 pieces. One is the outside of our bagel, which is the same as the figure knot complement. And inside, we have a bagel minus a circle, and which is known to be cipher fiber. Cipher fiber space is a kind of circle bundle over surface with some singularity. And you can easily see that this is a cipher fiber. So we have the JSJ unique decomposition of the knot complement, and this is hyperbolic, and the other is cipher fiber. So by definition, the volume of this knot complement is the volume of the hyperbolic piece, which is the same as the volume of the figure knot complement. So this is the definition of our volume, and this is the statement of the volume conjecture. So in particular, if the knot has no hyperbolic pieces, the volume conjecture states that the limit is 0. Now, for example,
torus knot has no hyperbolic piece. It consists of single fiber pieces. So the volumetric conjecture says that the limit is 0, and it was proved by Kashev and Tohoku.
Question.
Yes.
You can see that the right-hand side splits as a sum of the
Yes.
hyperbolic
Yes.
volumes
Yes.
and the zero volume.
Yes.
Does that happen on the left-hand side for the colored Jones polynomial? Can you split off the...
I don't know. How? Do you think you can?
There's no satellite formula.
No. It's a good question, but I don't know. It may happen.
Well, but it's not for the colored Jones polynomial. You are evaluating it at the root of unity. So to look for a formula for what happens under satellite for colored Jones may be too hard. What happens to the Kashev invariant for satellites? Is there a splitting off?
If you have such a formula, yes, but I don't think we have. Because one reason is that yes, so yes.
I'm just going to there is a satellite formula.
Well, I'm sorry, what?
There is a satellite formula for the colored Jones.
For the colored Jones?
Yes.
But it is.
I'll show you in my
Yes.
Okay.
It's complicated, but okay, yes. Roland will describe it. But it's not so simple. It's not the sum formula. It's rather complicated. Any more questions? So next I will give a complete proof of the volume conjecture. Unfortunately, only for the figure note by for the difficult. So yes, so this is the figure note, you see, and it is rather difficult to prove this closed formula for the figure note. If you know, starting with the braid, free braid, it is very difficult to get this formula because it is given by 4 summations. 2. Yes, we can reduce 2 because there are many Kronenker's delta, so we can reduce it to 2. It is not so hard, but to make it a single summation, it is very difficult. To do, yes, this formula is by Kazuo Habiro and Tanrei, and Kazuo Habiro used his scaling theoretical formula to get this formula, and Tanrei uses a kind of tangle formula, not a braid one. To start with the tangle, he get this formula. So I please skip this, the proof of this formula. And we prove the volume conjecture. We first replace Q with M through to unity. Yes. Sorry?
Can one use basic hydrogen geometric series?
No.
Yes.
Yes? It's very simple.
You can do it by computer. Rigorous.
What?
You can convert the double sum formula into a single sum formula by computer rigorously. You have to do things if you know.
So computer can do it.
This is the real type of algorithm for geometric sums. This is the basic So the problem is, the formula you get from the R matrices is a little more complicated when you convert it to that form. That's one way you can do that.
So
Yes. There is a book that explains, it's called A equals B. Capital A equals capital B. If you check, you'll see how to get these formulas without thinking.
Okay. So anyway, so suppose that we get this formula, and we replace Q with infinity, and then it is a single summation of product, and we. So if Q is the infinity, then it can be written as square of sine function. You see. So we get. So we have I here and I here. So we get I squared and. So anyway, we get positive. So note that F is always positive. So it is a sum of products of positive functions. And yes, this is the formula. And the first one, we find the maximum of this F function. So it is a function of K if it is N. And so this is the graph of F. So it is a square of sine, and K is from 0 to N minus 1. So the variable here is from 0 to 1. This is 1. So the sine squared is like this. And from this graph, we can see how the product, the graph of the product looks like. So because F is always positive, and it is smaller than 1 before n over n, n over 6. And it comes to 1 when J. Something's wrong. Yes, sorry, this is K. It should be K. When K is n over 6, it touches 1. And then it goes up over 1, and it goes to 1 when K is 5n over 6. And it goes down below 1 after that. So the J, which is the product of F's, is going down before n over 6. Because it is a product of numbers which is smaller than 1. So it goes down, and then it goes up, because we multiply by a number bigger than 1. So it goes up, and at 5n over 6, it attains the maximum. And then it goes down again. So we know that this, so when J is 5n over 6, it attains the maximum. So we know that the maximum of G function is attained at 5n over 6. And note that the Jones evaluated that infinity is the sum of this G function, which is always positive. So, because each term is positive, the sum is bigger than one term. And there are n terms, and the maximum is this one. So the sum is smaller than n times the maximum. So we have these inequalities. Okay. Then we take both and divide it by n to get these inequalities. Note that the product becomes summation after taking log. And then take the limit. I hope you know that the log n is much smaller than n. So this and this are the same. So we get the equality. these inequalities. Okay. So the limit of the log of the color choice over n is the limit of this g function evaluated at 5n over 6, the maximum of the summand. So now what we have to do is to calculate this limit. But this is g is a product of f functions, and so if we take log, it is a sum of log of f functions. And remember that f is a square of sine function, so it is just a log of twice of sine k pi over n.
That 2 should be log of 2 sine.
2 log of sine. 2 log sine. Two sine?
Yes. So 2 comes here and makes 4 and sine squared, which is the formula of f function. F function is 4 times sine squared.
Okay.
Now, then it is easy to replace the summation with usual Riemann integral. Here x is k5 over n. So because in a sense we change the variable, we need 1 over pi here, because usually we put k over n to be some variable. We replace k pi over n with x, so we need extra pi here. Then, so by definition, this is the Lobachevsky function, which is minus of this integral. By using this integral, by using the Lobachevsky function, our integral can be written as minus 2 over pi times the lambda of pi over 6. And by using, say, Mathematica, it tells you that the value is 0.323 or 66 and so on. Yes?
Do you have too many minus signs?
Sorry?
Do you have too many minus signs?
Too many what?
Are you sure about the minus signs?
Because sine starts at near 0. So it starts at minus, negative. So we need minus sign to make it positive.
So the Lobachevsky function 5 over 6 is negative.
Yes. But the value of the function is positive if theta is small, near 1. Because sine is smaller than 1. And if you take log, it is minus. So we need to change the sign to make it positive. Okay. Any other questions? Okay, so what is this? So we'd like to know what is this value, lambda of pi over 6.
Multiplying that by negative sign, you should get a negative number. No, up there.
Yeah.
Yeah. This is, it's negative 2 times
lambda. Sorry, you are, something is wrong here.
No, you're correct. It's just that the angle is pretty big that it becomes negative.
Okay. I think this is correct. I think this is correct. So, because pi over 6 is big enough, so it becomes negative again. So, what is, I'll tell you how to calculate the value. So, what is, so I will tell you some properties of the Lobachevsky function. This is the definition of Lobachevsky function, lambda of theta. And it can be easily seen that lambda is an odd function and has period pi because of the
we have absolute value sign here. So sine x has period pi, so it has period pi, and the integrand is an even function. So this is a odd function, and it has this kind of formula in general. So we can replace n times theta with smaller sum of these things. But the proof of this, the proof of the first one is quite easy, and for the second, we use the double angle formula of the sine. Do you remember? Double angle. Sine of 2x is equal to 2 sine x cosine x, and so we can go, and then this becomes, sine cosine of x is plus or minus sine x of pi over 2, but we have an absolute right sign here, so we don't need to mind which sign we take. So we have this formula. So by integrating these, we get this formula. So by using these, first, so we'd like to know this value, but by pi periodicity and oddness of the function, this is equal to minus of lambda pi 6. So, yes, so the lambda pi of 6 is positive. So this is it. And from this formula, when theta is pi over 6, we get this formula. And here we use pi periodicity and oddness of the function. So from these, we get the lambda of 5 pi over 6 is equal to minus 3 over 2 times pi of, lambda of pi over 3. Now, we get 2 pi of log of the Jones over n is 6 times lambda of pi over 3. Then, what is this? So we need some hyperbolic geometry. And the first, note that it is well known that the figure complement can be decomposed into two regular ideal hyperbolic tetrahedron. So the volume of the figure complement is the sum of the volumes of these two, which are equal, so twice of the volume of these regular ideal hyperbolic tetrahedron. And this part is done by Given, so I skip quickly. So the point is the volume of, that each hyperbolic tetrahedron can be parameterized by 3 angles, Euclidean angles. And in this case, we use regular tetrahedron, so every angle is pi over 3. And an important fact is that the volume of ideal tetrahedron parameterized by with dihedral angles alpha, beta, and gamma is given by the sum of Lobachevsky functions. And this formula can be proved by just integrating the metric by this kind of upper half space model. So it is not so hard to prove this. Now, because we have two ideal regular hyperbolic tetrahedra, so the volume of the complement is equal to 6 times, yes. So a regular ideal hyperbolic tetrahedra has volume 3 times pi, 3 times lambda of pi over 6. So the volume of the Euclidean complement is twice of this. So we need to divide by 10 here. Anyway, so the 2 pi of, sorry, we need log. 2 pi of log of Jn over n is equal to the volume of the hyperbolic complement. So this completes the proof of the Bernoulli at at least for the beginning. So, here's a just comment. So far, as far as I know, the volume conjecture is good for torus nodes. So as I told you, a torus node has 0 volume. So they proved that the limit is 0. And the second result is given by Kami, and the figure node is given by a coin. And I think in the case of 5-2 node, the proof is given by Kashet and Yokota. 5-2 node is, the second simplest hyperbolic node. I think Stoltzfus said something yesterday about 5-2. And how Chen proved the volume conjecture for the pointed doubles of torus. So pointed double is something like there's a clasp in torus node. So it can be decomposed into pointed ring complement and torus node complement. And also he proved it for twisted pointed ring. And I think Stoltzfus and Tande proved it for Brownian rings. And Roland and we proved it for. You did more?
Yes.
Okay. Maybe, yes, that's all. Yes, thank you.